Usually when we talk about how a mobile app handles data, there's this expectation of a very specific relationship.
Right, like a client-server dynamic.
Exactly. It's like a restaurant. You sit down, you place an order, and the waiter has to literally run out the back door, sprint all the way to a farm, which is the cloud, grab your specific ingredients, and then run all the way back to the kitchen to make your meal.
Which is incredibly inefficient if you think about it.
Oh, totally. But today's Wednesday, April 1, 2026, and we are looking at a stack of blueprints that completely redesign that restaurant. We've got official docs from React, Next.js, and MongoDB, plus some really specialized developer tutorials from Morrow Digital, Bean TA, and Vuelytics.
Yeah, it's a fantastic stack of sources.
We are talking about offline first architecture. Our mission for this deep dive is to unpack how to build a fully stocked, high velocity pantry right inside the kitchen on your phone. So, the waiter never actually has to leave the building.
And worse than that restaurant analogy, if the road to the farm is blocked, or say the cell service drops on a subway, the user is just sitting there staring at a blank plate.
Just a spinning wheel of death.
Exactly, or an infinite loading spinner. I mean, in a world of absolute information overload, decoupling the responsiveness of your UI from the latency of your network, it's no longer just a neat developer trick.
Right.
It is a fundamental requirement for user retention. If your app stutters because it's waiting on a server to resolve an image or a text string, that user is gone and they are not coming back.
Yeah, and if you are listening to this right now, you know exactly how high the stakes are. If you've ever wondered how enterprise apps scale to handle tens of thousands of records without a single dropped frame,
Which is incredibly hard to do, by the way.
right, or how they survive offline without losing your data, this is the deep dive for you. We are tearing down the entire stack today.
It's a phenomenal collection of material, really, because it bridges that gap between high-level architectural theory and the actual boots-on-the-ground implementation details you need to pull this off without losing your mind.
Okay, let's unpack this. To build this incredible in-house kitchen pantry, we need a solid foundation. The blueprints all point to React Native, but specifically supercharged by the Expo ecosystem.
Yeah, Expo's pretty much mandatory at this point.
Right, because we all know React Native lets you write JavaScript or TypeScript to render real native elements. But historically, dealing with the underlying iOS pod files and Android Gradle scripts has been pure agony.
Pure agony is putting it lightly.
If you've ever spent 3 days fighting Xcode build errors just to add a single dependency, you know the pain.
Oh, absolutely. And that underlying fragility is exactly why Expo's managed workflow has become the industry standard. Expo essentially abstracts away the native complexity.
Which is a lifesaver.
It really is. Our sources highlight tools like the Expo router, which brings file-based routing to mobile, heavily inspired by Next.js, actually.
Oh, nice.
Yeah, it drastically reduces boilerplate and automatically handles the really complex edge cases of deep linking. Then you have EAS, which handles cloud builds and over-the-air updates.
Oh, OTA updates are huge.
Huge, allowing you to basically bypass App Store delays for critical bug fixes.
Right, but there's a catch here. To get that robust, high-performance pantry we talked about, we need a serious database. And the star of the show today is WatermelonDB.
A fantastic piece of tech.
It is, but WatermelonDB is a heavy-duty native module. It relies on C++ and SQLite. In the old days, if you wanted to add a complex native module like that, you had to eject from Expo.
Yep, the dreaded eject.
You had to leave the safety of the managed workflow, crack open the native folders, and manually link everything.
And that used to be a complete deal breaker for smaller teams. But the documentation from Morrow Digital outlines a brilliant workaround. They created a package called the WatermelonB Expo plugin.
Okay, and this supports Expo SDK 50, right?
Yes, supporting Expo SDK 50, it leverages what are called config plugins. So instead of a developer manually writing native code, the plugin programmatically modifies the native Android and iOS build files during the pre-build phase.
That's wild. So it does it for you.
Exactly. When Expo generates the native folders, it injects the necessary native dependencies automatically behind the scenes.
But wait, I have to push back slightly here. If Expo is abstracting all this away with config plugins, aren't we just adding layers of, magic complexity that could randomly break during a production build?
It sounds like it, sure.
I mean, why not just bite the bullet, eject, and write the raw native code so you know exactly what the machine is doing?
What's fascinating here is that the config plugins actually reduce human error significantly. When you're dealing with a high-performance database like WatermelonDB, it requires linking very specific, highly optimized C++ libraries.
Okay, like what?
For instance, it uses a library called SymJSON, which leverages single instruction, multiple data operations to parse JSON at gigabytes per second.
Gigabytes per second. That's insane.
Right. Now, if a developer tries to link a C++ library like that manually across different development environments, say Apple Silicon versus Intel, varying OS versions, the chance of a misconfiguration is incredibly high.
Ah, okay. I see where you're going with this.
Yeah, by automating the native dependency linking at build time, Expo ensures absolute consistency across every single build environment. You get the raw metal power of native code without the fragility of manual human configuration.
That makes a lot of sense, actually. You lock in the configuration once, and the machine perfectly repeats it. So our foundation is solid. We can safely bring in heavy-duty native modules.
Exactly.
Now we have to address the data bottleneck itself. The Viewlytic source goes deep into why traditional data management tools completely fail when an app starts to scale.
And it all comes down to how these tools manage device memory. Traditional solutions like wrapping Redux with a persistence adapter or relying on async storage, they use what we call eager loading.
Meaning the app demands everything right at launch.
Precisely the issue. When the app boots up, it tries to read the entire database and load it into the device's active memory upfront.
Which is fine for a to-do app.
Right, if you have 500 records, you might not notice. But if you have 50,000 records, that eager loading can freeze the app for 2 to 5 seconds before the first screen even renders.
Especially on an older phone.
Oh, absolutely. It's brutal on older hardware.
It's like trying to memorize an entire 20-volume encyclopedia before you're allowed to answer a single, simple question. It's incredibly inefficient.
And that inefficiency destroys the user experience. This is exactly where WatermelonDB flips the script. It operates on a strict lazy loading paradigm.
Okay, lazy loading.
Yeah, it is built on a rock-solid site foundation, but it only queries and loads the exact data that the user interface is currently requesting to render on the screen.
Like an incredibly optimized index.
Exactly. You only look up the exact sentence you need exactly when you need it. And remarkably, adding this powerhouse C++ database to your app only increases the total bundle size by about 2 megabytes.
Just 2 megabytes. That's nothing. But the speed doesn't just come from the lazy loading, right? These sources spend a lot of time dissecting the React Native bridge and how WatermelonDB bypasses it.
Yeah, the bridge is the traditional bottleneck in React Native. Normally, JavaScript and the native device code communicate asynchronously over this bridge by serializing data.
Meaning they turn it into text.
Right, they take a JavaScript object, turn it into a JSON string, send it across the chasm, and unpack it on the native side. That serialization costs precious milliseconds.
Death by 1,000 cuts.
Completely. But WatermelonDB bypasses that entirely using JSI, the JavaScript interface.
So how does JSI actually solve that serialization delay?
Well, JSI allows the JavaScript engine to hold direct memory references to the underlying C++ objects.
Oh, wow.
Yeah, there is no stringifying, no JSON parsing across a bridge. It's the difference between writing a letter, mailing it, and waiting for a reply versus just tapping the person next to you on the shoulder.
That is a great way to put it.
Because JavaScript can directly invoke C++ methods synchronously, queries resolve in under a single millisecond.
Under a millisecond. That is absurd.
It is. If we connect this to the bigger picture, this direct memory access is how enterprise-grade applications actually scale. The documentation notes that apps like Nosby Teams use this exact architecture to manipulate tens of thousands of records without the user ever perceiving a delay.
But I imagine that takes some careful engineering.
Oh, it requires strict developer discipline. You have to implement proper indexing like indexing Boolean fields or foreign keys so the database engine doesn't have to sequentially scan every single row to find a match.
Right.
And you must batch your write operations. If you're updating 50 records, you wrap them all in a single database.write transaction.
Ah, so it processes as a chunk.
Exactly. The system processes one highly efficient block instead of 50 separate slow operations.
Okay, so we have this formidable near-instant database acting as our kitchen pantry. But here's the next logical hurdle. If I update a record in that database, say, a background sync pulls down a new chat message, how does the UI know to update without just reloading the entire screen and causing a jarring visual stutter?
Yeah, a fast database is completely useless if the UI can't keep up smoothly. WatermelonDB handles the synchronization using the WatermelonB/React package and a higher order component called with observables.
Now, a higher order component, or HOC, sounds like heavy jargon. But really, it's just a smart wrapper, right?
That is a perfect way to describe it. This wrapper essentially subscribes a specific UI element, like a text field or a button to a specific row in the database.
Got it.
Developers use decorators like @field, @relation, and @children to wrap their JavaScript classes directly to the underlying database columns.
And this is where TypeScript comes in.
Yes, TypeScript becomes non-negotiable here. It acts as a strict safeguard, ensuring that the properties the UI component expects perfectly align with the database schema.
So it catches errors before they happen.
Exactly. If they don't match, TypeScript throws an error during development, preventing those dreaded runtime crashes that plague so many mobile apps.
So because of this smart wrapper, the UI component is just passively listening to that specific row.
Yes, when a background think alters a record in the database, only the specific UI components wrapped and subscribed to that exact record will re-render. Everything else on the screen stays perfectly static.
That's incredibly efficient.
Imagine a highly active chat application with thousands of loaded messages. You can maintain a buttery smooth 60 frames per second scrolling experience because when a new message arrives, the app doesn't recalculate the whole list. It only renders the specific new message bubble.
Here's where it gets really interesting. If the database is this fast, and the UI is automatically observing it and updating surgically, does this mean we can completely throw away global state managers?
I know where you're going with this.
Like, do I even need Redux or the context API anymore for this kind of data?
For persistent data, absolutely. You can remove them entirely from your architecture.
Wow. Really?
Yes, the database takes over as the sole single source of truth. This is a profound paradigm shift. It drastically reduces the memory overhead of the app, and honestly, it significantly simplifies the developer's mental model.
No more writing complex reducers.
Exactly, you stop writing them to synchronize your UI state with your database state, because the database is the state.
That is incredibly clean. So the database is the state, and the UI components are reacting instantly. But there is another bottleneck we have to address to get that flawless 60 frames per second experience.
The styling.
Yes, performance doesn't stop at the database. If your UI styling is calculated at runtime, your app is still going to stutter when a user scrolls. How are we styling these components efficiently across iOS and Android? Because writing traditional style sheet objects in React Native is notoriously verbose.
It is painful, especially if you are transitioning from web development, but our sources highlight a tool that completely changes the rendering game NativeWind.
Which is basically Tailwind CSS, right?
Essentially, yes. NativeWind brings the utility-first approach of Tailwind CSS directly to mobile development.
So instead of writing out dozens of lines of custom CSS objects, you just use Tailwind utility classes on the components. But wait, if it's parsing those string classes while the app is running, doesn't that create the exact runtime stutter we were trying to avoid?
That is the genius of NativeWind's architecture. It does not parse strings at runtime. It compiles those Tailwind utility classes into optimized React Native style objects at build time.
Oh, so there is zero performance penalty while the user is actually interacting with the app.
None whatsoever. The styling logic is completely pre-calculated before the app ever hits the App Store.
That's brilliant.
Plus, it supports platform-specific modifiers right in the class name. You can write a class string like iOS:PT12 and Android:PT4 in the exact same line of code.
So no more messy if statements.
Right, it applies 12 units of padding on iOS and 4 on Android, which completely eliminates the need for those clunky JavaScript conditional statements that usually clutter up component files.
It's the difference between hiring a tailor to actively sew a suit while you are walking down the street, which is runtime calculation, versus having the factory pre-sew every possible outfit variation before the clothes even ship to your house.
I love that analogy.
NativeWind's doing all the heavy lifting at the factory.
That is exactly the mechanism at play, and it scales beautifully. By combining NativeWind with CSS variables, developers can instantly enable dynamic, system-aware dark modes, or completely swap out brand themes across the entire app with a single variable change.
And it processes instantly.
Instantly because the underlying styles are already compiled.
Now, there is a very specific setup quirk mentioned in the DEV community source that we need to point out for anyone actually trying to implement this blueprint today.
Yes, a crucial detail. Currently, the stable version of NativeWind requires developers to install a very specific version of Tailwind,
Which is?
Tailwind CSS version 3.3.2. If you try to use the newer version 4, the compiler will break.
Yikes.
It's a temporary architectural quirk, but it's exactly the kind of undocumented friction that can waste hours of a developer's time.
Save yourselves the headache. Okay, let's step back. We've eliminated the data bottleneck with WatermelonDB. We've eliminated the styling bottleneck with NativeWind. The app is incredibly responsive.
It's flying.
But what happens when you hit a subway tunnel? What is the point of a hyper-optimized mobile app if it turns into a useless brick the moment you lose cellular service? Let's talk about the synchronization protocol.
This is arguably the most complex but most rewarding part of the entire architecture. In an offline first app, the cloud server is still the ultimate master source of truth.
Okay.
But the local client, your phone, has a full, working, interactive copy of the data it needs to function independently.
So how do they talk to each other without creating absolute chaos when the connection comes back?
It's a strict two-phase protocol, pull, then push. First, the pull phase. The client app sends a last pulled at timestamp to the server.
It essentially says, here is the exact millisecond I last spoke to you.
Exactly. The server evaluates that timestamp and sends back every single change that has happened globally since that exact moment. WatermelonDB ingests that payload and updates the local pantry.
So pulling is easy. It's just grabbing the delta. But pushing local changes back to the server feels like a minefield.
It definitely can be.
Say I update a task's title while I'm on an airplane without Wi-Fi, but someone else on my team updated that exact same task's description while I was offline. When my phone reconnects and tries to push, how do we avoid overwriting someone else's work?
WatermelonDB handles this elegantly using a strict per-column client wins strategy.
Per column.
Yes. In your scenario, the server's version of the record is generally accepted as the absolute truth, except for the specific columns you modified locally since the last successful sync.
Oh wow.
So during the merge, the system will accept their new description from the server, but it will forcefully apply your new title over the old one. It resolves the conflict at the column level rather than blindly overwriting the entire row.
That is brilliant. It preserves everyone's work seamlessly. Now, what does the backend look like to support this kind of granular merging?
The sources outline two highly effective paths. The tutorial from the Bond Studio demonstrates using Superbase, which leverages a Postgres database.
Okay, Postgres.
They use Postgres RPC's remote procedure calls. What this means is that they write custom functions that live directly inside the database itself.
Bypassing the middleman.
Exactly. This allows the client to handle the entire pull and push logic in just two simple database calls, rather than hitting dozens of different REST endpoints. All the heavy lifting, including that complex conflict resolution, happens natively inside Postgres where it is fastest.
And the architectural analysis provides a different route.
Yes, the alternative uses a Next.js app router server acting as a secure synchronization gateway to a MongoDB backend.
So mapping SQLite to Mongo.
Exactly, and this approach is fascinating because it maps the strict relational row and column data of the local SQLite database into MongoDB's highly flexible JSON-like document model. Next.js handles the authentication and business logic, while MongoDB handles the massive scalable storage.
But wait, I have to point out a major flaw mentioned in the sources, specifically in the Baltet blog.
Oh, the schema migration issue.
Yeah, the author admits a huge drawback to this whole offline-first approach. If I want to change my data model, say I want to add a simple priority field to that task, I have to update the Superbase Postgres schema, then I have to update the local WatermelonDB schema on the app, and I have to rewrite the push and pull sync functions to recognize the new field.
It's a lot of steps.
Isn't that an insane amount of friction just to add one single column?
This raises an important question, and the author is entirely correct about the friction. It is a substantial amount of overhead. But you have to understand that offline first is a deliberate architectural trade-off.
How so?
You are consciously sacrificing developer convenience and rapid prototyping speed. In exchange, you are gaining absolute bulletproof reliability and zero latency speed for the end user.
Right.
This stack is designed for mature, stable applications where the user experience is paramount, not for weekend hackathons where the data model changes every 3 hours.
Okay, let's unpack this and summarize the whole deep dive. By combining the safety and automation of Expo's managed workflow, the incredible lazy-loaded JSI speed of WatermelonDB, the zero runtime overhead styling of NativeWind, and a robust push-pull synchronization engine, you could build an application that feels impossibly fast.
Truly frictionless.
It reacts instantly to changes, and it absolutely never leaves the user hanging without a connection.
It truly represents the gold standard of current mobile engineering.
So what does this all mean for you? It means that choosing this stack is a philosophical decision. You are explicitly deciding to prioritize your user's experience and their data security over your own immediate convenience as a developer.
Spot on.
You are doing the hard, tedious work of defining strict schemas so they never have to wait for a loading spinner.
But I want to leave you with one final thought, something that wasn't explicitly covered in the blueprints, but is the logical horizon for this technology.
Oh,
We saw MongoDB mentioned in the stack, and they are pushing heavily into AI and vector search. We are moving toward a near future where AI starts dynamically generating personalized interfaces and entirely new data structures on the fly, uniquely customized per user based on their behavior.
wow. Okay, that breaks the whole model.
Precisely. So the question becomes, how will strict, hard coded synchronization schemas like WatermelonDB adapt to a world where the data model itself is completely fluid?
Right, because if it's changing dynamically.
Exactly. Will we eventually need a local database that doesn't just sync data offline, but can actually negotiate, evolve, and mutate its own schema without an internet connection, driven entirely by a local on device AI? It's a fascinating engineering challenge that is coming sooner rather than later, something to mull over.
That is a wild thought to end on. At self-mutating offline pantry. We started this deep dive talking about a restaurant where the waiter never has to leave the building because the pantry is perfectly stocked.
A Michelin star setup.
Exactly. It turns out building that pantry takes incredible precision, strict rules, and a lot of upfront architectural work. When the customer gets their meal the exact millisecond they ask for it, well, that's what earns the Michelin star.
Beautifully said.
Thank you for joining us on this deep dive. Keep exploring, keep building, and we'll catch you on the next one.